Space-time travel, the concept of journeying through both space and time, has long captured the human imagination. From ancient myths to modern science fiction, it's a topic that fascinates and intrigues us. In the realm of scientific theories, the discussion of space-time travel primarily revolves around Einstein's theory of general relativity and its implications. General theory of relativity. Albert Einstein's theory of general relativity, formulated in 1915, revolutionized our understanding of gravity. According to this theory, gravity is not just a force between masses, as described by Isaac Newton, but rather the curvature of space and time caused by massive objects. This curvature is what we perceive as the force of gravity. General relativity predicts the existence of phenomena like black holes, gravitational waves, and the bending of light around massive objects. Space-time. General relativity posits that space and time are interconnected in what we call space-time. This means that any massive object, like a planet or a star, warps the fabric of space-time around it. The greater the mass, the greater the curvature. This curvature affects the motion of objects, causing them to follow curved paths through space-time. Wormholes. One of the most intriguing possibilities for space-time travel arises from the concept of wormholes. A wormhole is a hypothetical tunnel-like structure that connects two separate points in space-time. In theory, traversing through a wormhole could allow for instantaneous travel between two distant locations or even different points in time. However, the existence of wormholes remains purely theoretical, and their stability and practicality for space-time travel are still under investigation. Time dilation. Another consequence of general relativity is time dilation, which occurs when an object is moving at speeds close to the speed of light or in strong gravitational fields. Time dilation means that time passes differently for observers in different reference frames. For example, astronauts traveling at high speeds or near massive objects experience time passing more slowly relative to observers on Earth. This effect has been confirmed experimentally through various experiments, such as the famous Hafele-Keating experiment involving atomic clocks. Quantum mechanics and space-time. Integrating general relativity with quantum mechanics, the theory that describes the behavior of particles at the smallest scales, remains one of the biggest challenges in theoretical physics. While general relativity provides an excellent description of gravity on large scales, quantum mechanics governs the behavior of particles on tiny scales. The unification of these two theories into a single framework, often referred to as quantum gravity, could potentially provide further insights into the nature of space-time and the possibilities for space-time travel. In summary, while the concept of space-time travel is rooted in theoretical physics, particularly general relativity, it remains speculative and subject to ongoing research and exploration. While we have made significant strides in understanding the nature of space-time and its relationship with gravity, practical space-time travel, especially for human beings, remains a distant prospect awaiting further scientific breakthroughs.